Welcome to this second lecture on concept of image impedance. Now, I hope you agree with me that any two-port network can always be represented by either a T section or a pi section. Without losing generality, I take that my two-port network, that means that transmission line parameter transmission matrix characterization is ABCD, that is a T section. The same analysis holds for a pi section. So, now I have that T section this is Z1, this is Z2, this is Z3, all these are impedances, complex impedances. So, this is my port 2, this is my port 1, this is the internal description of the network. Now, I want that when I will excite the port 1 with that voltage Vs and I have some internal impedance, let us call that internal impedance Zi1. Last time I called it Zs, this time I am calling it Zi1, it is simply change of nomenclature. So, this is my port 1, this is my port 2. Now, you see all of you are familiar with maximum power transfer theorem. Maximum power transfer theorem says that if the load impedance is a complex conjugate of the source impedance, then maximum power gets transferred. I think you have noticed that in low frequency, particularly these VLSI people etc., when they work up to gigahertz range, they do not give any consideration to this maximum power transfer theorem, because in baseband, unless you go up to radio frequency and transmit it, you have plenty of power. So, you are more concerned with your voltage maximization. That is why you design a good C amplifier with very high voltage gain, but voltage gain does not necessarily mean maximum power gain. But when we go to radio frequency, we know power, microwave power is very precious. To produce microwave power, lots of complicated circuits are required. So, also when power is received by a receiver in radio frequency, it is very small amount. So, it is life and death for RF engineers or RF circuits to maximize power. So, maximum power transfer theorem always is in the design of RF circuits, always we try to pay regard to the maximum power transfer theorem. So, can I have this whole thing, suppose this I will terminate by some load impedance, let that load impedance is called Zi2, this one I call Zi1 source impedance, this is Zi2. Now, the idea of image impedance is at this point, obviously if I look at, I will get some impedance. Now, if this impedance is equal to Zi1, then I can, from the source, I can have maximum power transfer. Okay. Now, according to maximum power transfer, I suppose this I am looking at some Z in or something, Z in. Now, if Zi is complex conjugate of Zi1 star, then I know that maximum power transfer will take place. But as I said that our consideration now is filter, which is lossless network. So, this Z1, Z2, Z3, there is no R involved here ideally. So, they are complex, but they are generally they will be either real or not real, either all of them will be pure imaginary terms, they will be pure reactances. So in that case, I say that now I say that I will look into here at Zi1. Then Zi1 is equal to Zi1, not complex, not suppose any complex conjugate for pure imaginary things, it is equal. As you know that suppose I have two complex number, A is equal to B star. Suppose A is a complex number, B is a complex number. If A is pure real and B is pure real, then I can say A is equal to B. Similarly, if A is pure imaginary and B is pure imaginary, then only I can say A is equal to B. Since we know that this will be my, all these are pure reactances, this may be a pure resistance. So that's why I can call that my demand is Zi1 here should be equal to Zi1 here. That means source impedance and this input impedance looking at this port should be equal. But you see this Zi1 is a function of this load resistance Zi2. But now, so why it is called, this Zi1 is called image impedance. If I can find an impedance, load impedance Zi2, so that if I terminate this network, this is already given network, and I look at here and see that the input impedance is Zi1, then I know that I can transfer maximum power from this source to this network, this to this port 1 of this network. Now why Zi1 is called an image impedance? Because if at this plane I look, so I looking at this side I am getting, to the right side I am getting an Zi1, looking at left side I am seeing the impedance as Zi1. So this side is an image of this, that's why this is an image impedance. So Zi1 is an image impedance. Same thing here, that here I want that if I look at here, I should look at some output impedance that should be equal to Zi2. So at port 2, if I look to this side I am getting Zi2, if I look to this side I should get Zi2. So if I can find this pair Zi1, Zi2, so that if I terminate by Zi2, then I get here Zi1 impedance. Similarly here, if I terminate by Zi1 and excite here, I should see here a Zi2. These two pairs are called image impedance. Since this is an asymmetrical network, because Z1 is not equal to Z2, I will have two impedance Zi1 and Zi2. Let us see that whether this image impedance can be represented in terms of this impedance of this network. So the same diagram, I can write that Zi1, or do like this. So this Zi1 I can write as, what is Zi1? Obviously it is Z1 plus, you see, Z3 parallel to Z2 plus Zi2. Likewise, what is Zi2? It is Z2 plus Z3 parallel to Z1 plus Zi1. Now these two equations, you see Zi1, here I have Zi2, I have Zi2, here I have Zi1. I have two equations, so I can solve for Zi1 and Zi2 in terms of Z1, Z2, Z3. If I do that, upon solving this, I get Zi1 is equal to root over Z1 plus Z3 into Z1 Z2 plus Z2 Z3 plus Z3 Z1 by Z2 plus Z3, and Zi2 is Z2 plus Z3 into Z1 Z2 plus Z2 Z3 plus Z3 Z1. So, you see that these image impedances can be represented in terms of the component impedances of the T section. Now, always we won't be knowing Z1, Z2, Z3. As I said that let us consider two-port network as a black box, but we can do measurements and always find these image impedances. How? You know that any measurement requires either an open circuit or short circuit of the one of the ports. So, for any impedance measurement you need to do this. Also you have seen that if you want to find any two-port parameter, you need to have some port condition, either short, open, etc., etc. So, if we measurement of image impedance, let us say that port 1 we measure impedance when port 2 open. We call that measurement as Z1, since we are doing at port 1 open circuit. Z1 OC means I am measuring the impedance, input impedance at port 1 with port 2 open. So, if we look at the circuit, if I open circuit this, what will be Z1 OC? It will be simply Z1 plus Z3. Similarly, if we measure impedance at port 2 with again port 1 measure impedance when port 2 is shorted. Now, let me short this port. So, I call Z1 SC, second port is shorted. You look at the circuit, if I short it, it will be Z1 plus Z2 Z3 parallel. So, Z1 plus Z2 parallel Z3. Okay. Now, what is this? This is Z1 Z2 plus Z2 Z3 plus Z3 Z1 by Z2 plus Z3. Now, you observe the image impedance terms. Already I have solved Zi1. Can I just compare? Can I say that Zi1 is equal to Z1 OC into Z1 SC? So, by measurement I can always find Z1 OC, I can find Z1 SC. I know what is the image impedance, immediately I can calculate from this. Similarly, instead of port 1, if I measure in port 2 by once open circuiting port 1, find the input impedance at port 2, and then again you short the port 1 and measure the input impedance in port 2. So, port 2 things if we do, you will see the same thing, that Zi2 can be expressed as Z2 OC into Z2 SC. So, this shows that image impedances can be always obtained from short or open circuit measurements on any network. So we can easily do this. Suppose I am given a network, I can always find this Z1 OC, Z1 SC, Z2 OC, Z2 SC and find out this Zi1 and Zi2, and then accordingly I choose a source with that internal impedance Zi1 and terminate the or choose the load as Zi2. I know I can achieve maximum power transfer. Already I said, so that means I can have maximum power transfer is guaranteed if I use image impedance as the terminating impedance at both the ports. Now, we know, we have said that we will be using the two-port network as only lossless components. That means we won't use any R. So there won't be any internal loss there. So by terminating with image impedances, I assume maximum power transfer, no loss in the circuit, lossless. So image impedance is an important thing, a performance measure of the power transmission that is taking place to a network. So you see that we can specify something on it later when we will design a filter. So instead of ABCD, we can specify image impedances, and that will solve many of our problems. But think one point, that I have image impedance here, I have image impedance here. Also you see, with this I require to know that okay, I by this Zi1 and Zi2 terminations, Zi1 here, Z2 here, I have ensured that I am giving maximum power I am delivering to this load. But I am assuming that here there is no loss, but the power is flowing in this direction. It may so happen, since I am using reactive elements, power may be locally confined, that is not flowing there. So I need to also see how propagation is taking place inside this two-port network. So we need to have the transmission of power through the network also. That we will next see, that this is called propagation of power. So what we define, that again two-port network, I have this V1, I have V2, I have I1, I have I2 as before. Now let me define V1 I1 by V2 I2. Vi is volt ampere, the concept you have learnt in your electrical circuit class. So input volt ampere, these are complex quantities, input volt ampere and output volt ampere. What is this ratio? That will be something. Now I want to ensure that that is fully making the power transmission possible. So we call this, I can name it any number, this will be some number, you see, input by output volt ampere. But we have certain advantage if we, instead of defining any number here, we write it as some exponential factor e to the power 2 gamma. Why? Because you see, when I will cascade many such networks, this one will have some, this ratio e to the power 2 gamma 1, this will have e to the power 2 gamma 2, another will have e to the power 2 gamma 3, etc. Now from this input to this input, if I want to find what is this transmission ratio of volt ampere. If I express it in exponential factors, the final thing will be e to the power 2 gamma 1 plus 2 gamma 2 plus 2 gamma 3. But if I don't use this exponential factor, if I just write it as gamma, suppose, then I will have to work out and I will have to find out what is the magnitude and phase, all these things here. But exponential factor makes simply this is an addition. If it is an absolute value, it would have been some multiplication. We always prefer addition to multiplication. That's why initially people did like that, they put this as propagation constant, but now after some learning, people understood that if we represent this ratio as exponential factor, and also you see I have taken a factor 2 here. Why? Because many times we will be interested to see what is the voltage ratio, what is the current ratio, but this is actually a volt ampere ratio, which is, for that it is actually product of voltage and current. So, I have taken 2 gamma. This gamma is called propagation constant. So, what is the definition of propagation constant? You see, gamma is equal to half ln V1 I1 by V2 I2, a very, very important definition. Propagation constant, you see, it shows that how input power is propagating through the network, inside the 2-port network. So, my job is now to find out what is this e to the power 2 gamma ratio is equal to V1 I1 by V2 I2 is equal to, in terms of ABCD parameter, A V2 plus B I2 into C V2 plus D I2 by V2 I2. Also, I know V2 is equal to Z I2 image impedance. It is terminated with image impedances. So, if you do that, finally you can solve that this ratio will turn out to be this simple manipulation. Put this and you know the values of ZI1, ZI2. So, you will get this will be simply this, or e to the power gamma is equal to root AD plus root BC. Now, here you see this propagation constant I have expressed in terms of ABCD parameter. One more thing is remaining. I have already said about characteristic impedances. Is characteristic impedance also expressible in terms of ABCD parameter? Let us see. I have the same 2-port network. I have I1 here, I have V1 here, and I want that this should be ZI1, and here this should be terminated by ZI2, and this is V2, this is my I2. So, I can write, I know this is ABCD. So, V1 I1 is equal to A, B, C, D, the definition of transmission parameters. Also, I have V2 is equal to I2 Z I2 and V1 is equal to I1 Z I1. So, put these equations and find out what is Z I1. You will see, you will get A Z I2 plus B by C Z I2 plus D. Let me call this for time being equation 1. Now, reverse the picture, that same transmission line, this time I am putting the excitation here. So, I am looking at it, here I will get ZI2 and this is my V2 dashed as before, this is my I2 dashed as before, and from here I am taking terminating it with Z I1. This is my V1 dashed, this is my I1 dashed. So, here again I can write that V1 dashed I1 dashed is equal to A, B, C, D, V2 dashed minus I2 dashed. And what about the ports? V1 dashed is equal to Z I1 dashed, V2 dashed is equal to Z I2 dashed. Then find out that what is your Z I2. So, or you find out what is your Z I1, which is nothing but V1 dashed by I1 dashed. That will turn out to be A Z I2 minus B by minus C Z I2 plus D. So, this let me call equation 2. You have equation 1, you have equation 2. Solve for Z I1. If you solve, you will, so from 1 and 2 you can solve for Z I1, and that will be equal to or Z I1 will be equal to Z I1 will be equal to AB by CD, and Z I2 will be equal to root over BD by AC. Now I am happy because I know that Z I1, one of the image impedance, can be expressed in terms of 4 ABCD parameters. Z I2 also I can express in terms of ABCD parameters, and I have already seen that propagation constant gamma, you see this propagation constant, that also I can express in terms of ABCD parameters. ABCD parameters completely characterizes a two-port network. I say equivalently I can say two image impedances Z I1, Z I2 and e to the or and gamma, these three also characterizes a network. But what is the beauty? If I have Z1, Z I2, I know what is the impedance level of the excitations of the network. That means what is the source impedance, what is the load impedance, they are according to the power matching, so that no maximum power, they are according to the maximum power transfer. So, power will flow, and by putting conditions on gamma, I will be able to say whether this frequency will pass or not. So, instead of ABCD parameters, this is a better description of a two-port network if I want to design a filter. And already I have seen that I can do the measurement of image impedances. That time I said in terms of the by opening and shorting the port. I will also have to prove that I can do this for propagation constant also, because this is a new thing, that time I did not say this. So, that I will do now, that measurement of image impedance and propagation constant. So, what we will do, the same network, this is port 2, this is open circuit, and I am looking here at, let me call this Z01. So, I know V1 is equal to AV2 plus BI2, I1 is equal to CV2 plus DI2, etc. And open circuit means I2 is equal to 0. So, if you enforce that, this ZO1, that will be A by C. Then you short circuit, so or open circuit this port, the first port you open circuit and measure here ZO2. So, ZO2, that will turn out to be D by C. Then you do that short circuit port 1 and measure from this port you measure ZS2. You will see ZS2 will turn out to be B by A, and which one I missed? ZS2, ZS1, ZS. So, you short circuit this port and measure here ZS1. ZS1 will be B by D. Once you have that, you can immediately write, because already we have seen ZI1 is equal to the ZO1 into ZO2, etc. So, you will get that this is equal to AB by CD, and that is nothing but ZO1 ZS1. Similarly, ZI2 is equal to root over BD by AC, and that is D by C into B by A, and that is nothing but ZO2 ZS2. And you see what is tan gamma, tan hyperbolic gamma. All of you are familiar with hyperbolic functions. So, this is e to the power gamma minus e to the power minus gamma by e to the power gamma plus it, and that is nothing but BC by AD, that is ZS1 by ZO1 and or ZS2 by ZO2. So, you see that gamma can be expressed completely in terms of short circuit and open circuit measurements. So, I can measure image impedances by open circuit short circuit measurements. I can also measure gamma by open circuit short circuit measurement. Previously, I showed that ZI1, ZI2 and gamma, they completely characterizes as network, reciprocal two port network. Now, I have shown that they also can be measured. So, you do not have any difficulty. Any two port reciprocal network, lossless network, you can represent like this. So, an alternate description or characterization of two port network is in terms of ZI1, ZI2 and gamma. I think in the next class we will introduce another criteria called symmetrical network, and we will simplify this procedure. Thank you.